All right. Good morning. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
How are you guys? Fine? I hope all of you are good today. So again, today we are going to continue our lesson. So this is the second week, but unfortunately we missed 2 hour FICON because of the holiday on Tuesday. But I'm planning to make this 2 hour because we have 2 hour today. One of them is FICON, one of them is a non-FICON normally, but I'm planning to make 2 hour FICON. I think it's not a big problem for you, right? Because we have to replace the 2 hour that we missed last Tuesday. So we're going to have 2 hour FICON lesson for today. Yeah. All right. Let me check now. 14 students. We have some problem with signal unstable for this day. Yeah, starting from yesterday, I also have a big problem with the signal. Now also the same. Now I'm not using my Wi-Fi. I'm using my handphone tethering because the Wi-Fi is not stable. Inshallah, the tethering is stable. Yeah. Now is 16 students already joined. Let's start with the review what we did last week. Anyone want to give a review about what we learned last week? You can raise your hand and turn on your microphone. Anyone? Come on, guys. There is different name now. One of them is, please check your name. It is through your name because I saw different name here. I think the Zoom setting is still different. Does everyone check your Zoom name so I can see, and please turn on your camera if you don't have problem. All right, please raise your hand. Who want to make a review? Okay, Vishnu, please.
So last week we learned about fraction moles, molarity, and not molarity, but we learn about fraction moles and molality.
Yes.
And also we learn one of the colligative properties, which is vapor pressure lowering.
Right.
Uh,
Vapor pressure lowering. We start already with this one, yeah, but we couldn't finish yet. Okay, I told you that I'm going to review again about this. Okay, so let's do again the review. Okay, some of you have problem with the signal, I think, with the connection. So you can turn off your camera if you have a connection not stable. Maybe I will have also the same problem, but inshallah not. But if I have same problem, so I have to turn off my camera also maybe. Okay, so we were talking about the lowering vapor pressure last week. All right. So which one is the colligative properties? The lowering vapor pressure or the vapor pressure?
Lowering vapor pressure.
Very good. The lowering vapor pressure is the colligative properties, but the vapor pressure itself is not a colligative properties. Vapor pressure is not colligative properties. Like I explained to you last week, remember, yeah, how we define the vapor pressure when we have a closed system. Remember, we have to think about the closed system because we are talking about vapor, because when you open the system, the vapor cannot be measured. Yeah, so that's why we have to talk about the closed system. When we have closed system, full of water, what happened, guys? There is two processes happening: the water vapor, but at the same time the water condense, and these two processes are happening simultaneously at the same time. And what we call this process, when vaporization and condensation happening simultaneously at the same time?
Dynamic equilibrium.
Very good. So we learned about this one last year, about the equilibrium, and it is a kind of equilibrium, yeah, and it is dynamic equilibrium. I mean, dynamic means that it's always happening, yeah, it's moving actually. But what you see that the water, the amount of water is not changing. But actually, it is not like that. The water is always changing simultaneously. The water vapor and then water condensed vapor, condensed vapor, condensed vapor at the same time simultaneously. So it's changing actually, but because it's dynamic equilibrium, so you cannot see the changing. Yeah. So this is the concept of dynamic equilibrium, and we say that the vapor inside this process, when we have this condition, the vapor in here, the pressure that exists at here, the vapor pressure that exists here in this condition, it is called as vapor pressure, isn't it? And this is not colligative properties. Again, I want to mention that this is not a colligative properties, because the colligative properties that we're going to see is the lowering vapor pressure. Now, we're not talking about the lowering vapor pressure still we are talking about vapor pressure. So this is the definition of vapor pressure. All right, it is clear, yeah, up to here. All right, now let's think about a solution. Larutan, ya. How many components solution have?
2.
Who say 2?
Vishnu.
Vishnu. What are those 2 components?
Solutes and solvent.
Very good. Solute and solvent. Jangan hanya Wisnu yang menjawab ya, yang lain juga harus aktif. Nanti poin plusnya untuk Wisnu semuanya. Alright, solute and solvent. Thank you, Wisnu. But Wisnu, please, if you see that nobody answer, you can answer. Okay. Solute and solvent. Thank you, Wisnu. In bahasa we call it zat terlarut dan pelarut. Yeah. So the colligative properties of the solution. Yeah, we're talking about colligative properties of the solution. So we're not talking about colligative properties of solute or solvent. We are talking the colligative properties of solution. That's why we have to think about the solution that have 2 components, solute and solvent, right? Now, in learning about lowering vapor pressure, there is one scientist that experiment about this. The name of the scientist is Raoult. Bukan Raul ya, Raul Gonzalez. No, it's Rolt. I don't know, the exact name is Francois Marie Rolt. I don't know this guy is coming from which country, but it is a chemist. He made experiments about the vapor pressure. What he did again, he made a closed system, because they are working with vapor. In a closed system, he has solution, and the solution is have two component. The component of solute, the first one, let's say the solute A, and the component of solvent, yeah, and let's say that the solvent is S, yeah, it has solute A and solvent S. What Rolt say about this condition in his experiment? He said that the vapor pressure of A, yeah, this A, yeah, the vapor pressure of A is equal to XA. What is X? We learn about mole fraction of A times the P0 of A. What is P0 of A? P0 of A is the vapor pressure of pure A. Pure A artinya apa? Pure artinya dia sendiri, murni, only A. Only A, it has vapor pressure, and that vapor pressure is called as a P0A. But PA here is the vapor pressure of A in the solution. So it is not pure in the solution. Jadi ini sudah bercampur dengan S, dengan solvent. So PA is vapor pressure of A in the solution. P0A is the vapor pressure of pure A. Yeah, that's the difference. And we know XA is mole fraction of A. Mole fraction of A. So this is what Rolt find in his experiment. He found that PA is equal to XA times P0A. And it is also valid if we are talking about the solvent. Yeah, if we are talking about the solvent, so P solvent will be equal to X solvent times P0 solvent. It is also valid for the solvent, not only for A. Right? Is it clear? Everyone? Up to here, clear? Okay. You can write this one in your notebook or finish already? Finish? Can I erase?
Yes.
Yes, I will erase all of them. All right. I erase. Okay, let's continue. Now we are going to make an assumption because we are going to derive formula. Let's make an assumption. Let's assume that if solute A, I'm still continuing about this Rolt experiment. Yeah, if solute A is difficult to vapor. Kalau kita asumsikan zat A itu pelarut A, zat terlarut A-nya itu it's difficult to vapor, susah untuk menguap, jadi nggak ada tekanan uapnya. So A will not have vapor pressure because it's difficult to vapor. So now what I've got? What will be the P solution equal to? A P solution will be equal to the P what? Kalau A-nya, if the A is difficult to vapor, then the P solution will be equal to what? In the solution, we know that we have PA and P solvent, right? In the previous slide, remember, in the solution, we have two components. We have A and solvent, A and S, and we have PA and PS. Now, if we assume that A is difficult to vapor, so there is no PA, nggak ada PA-nya because it's difficult to vapor. So P solution will be equal to what? Say something.
P solvent only.
Yes, very good. Thank you, Andika. So it is only P solvent now because A is difficult to vapor. So we got this what condition when P solution is equal to P solvent when we have a solute A is difficult to vapor. For example, what? For example, if I have salt with water, salt is the solute, water is the solvent. Salt is difficult to vapor, but water is vapor. So when I mix the solution, salt and water, P solution is actually P solvent because the salt is difficult to vapor. Yeah. So we got this what kind of what we say that relation, solution and solvent. And remember again what Rolls said. What Rolls said about P solvent? Rolls said that P solvent is equal to X solvent time P0 solvent, isn't it? According to Roth law, Roth experiment. So now I get this relation P solution equal to X solvent times P0 solvent. Now my question is, this is a very critical question. Which one will be bigger, P solution or P0 solvent? Which one will be bigger? All right, say something. Which one will be bigger, P solution or P solvent, P0 solvent, sorry.
I think P solvent.
Who say that? Who's saying?
Lutfi, sir.
Lutfi, you think that the P solvent is bigger than P solution? Why you say like this, Lutfi?
Because in the fraction mole of solvent, we know that fraction mole of solvent is the mole of solvent over mole of solvent plus mole of solute. So it is less than 1.
All right, thank you.
More than.
We learned that from last week that the X is always less than 1, isn't it? Any X, any mole fraction of A, mole fraction of solvent is always less than 1. So if it is less than 1 here, so obviously P0 solvent will be bigger than P solution, isn't it? Thank you, Lupi, for the answer. Very good analysis from Lutfi, and I think it is a very simple analysis, and everyone can understand this one because X solvent is always less than 1. So P solvent will be bigger than P solution. So from here, I will get delta P then. Why I got delta P? Because solvent is always bigger than solution. So delta P will be equal to P0 solvent, the one which is bigger, minus P solution. Isn't it? Then if I want to find delta P is equal to P0 solvent minus P solution. Karena P0 solventnya pasti lebih besar daripada P solution. Right? Is it clear? Now this delta P is we call as the lowering vapor pressure. Ini baru yang koligatif. This delta P is the lowering vapor pressure. All right? Okay. I want to underline, or I want to make a what we say a star for one formula here, because we have so many formula here, but which one is important? This formula is important. So I make star for this formula. This delta P formula we are going to derive later. Ini harus di-derive lagi ya, harus diturunkan lagi. I have to derive again this one. And we are going to, from this derivation of this formula, we are going to have the second important formula. But the first important formula is this. P solution is equal to X solvent times P0 solvent. Please keep on your mind this. For this, what we say, formula. To find the vapor pressure of the solution is equal to the mole fraction of solvent times the P0 of solvent. Okay, is it clear? Can I erase this? Did you finish to write? All right, let's clear again this one and continue. Okay, I told you that I'm going to derive this formula. Delta P is equal to P0 solvent mulai melambat minus P solution, isn't it? Ini yang mau saya bilang, saya mau derive again from this formula. Okay, we are going to make just simple mathematical calculation and mathematical trick in deriving this formula. So please see carefully and try to understand the mathematical operation in here. It's very simple actually, pelajaran SMP ya, substitution and elimination, substitution, elimination, just something like that. Okay. We're going to start with this formula. Delta P is equal to P0 solvent minus P solution, and equal to P0 solvent minus what we have about P solution before in the first formula that I made star. The first formula that I made star is P solution is equal to X solvent, isn't it? Time P0 solvent. So I'm going to put this in here. So I'm going to open the parenthesis is equal to X solvent time P0 solvent. Still, we are assuming that the A or the solute is difficult to vapor, yeah, because in colligative generally we are going to see that the solute is always difficult to vapor. Okay, all right, I'm going to continue to open this formula, so it will be equal to P0 solvent minus, now can I open this one into X solute? Bagaimana kalau saya rubah jadi X solute? X solvent plus X solute is equal to what?
1.
1. Very good. So X solvent is equal to 1 minus X solute, isn't it? All right, so I'm going to put in here. X solventnya saya rubah menjadi 1 minus X solute. So 1 minus X solute times P0 solvent. I close the parenthesis. All right. So I'm going to open again this one. So is equal to P0 solvent minus 1 time P0 solvent. It is P0 solvent minus P0 solvent time X solute, isn't it? Or X solute times P0 solvent. Parenthesis close. Right, let's continue to rearrange this equation. So P0 solvent minus, I open this parenthesis, minus again P0 solvent. Now minus and minus become plus. Plus X solute gimana? Minus X solute times P0 solvent, isn't it? Yeah. Okay, now the parenthesis is open. Now what we get here? Apa yang bisa kita lakukan sini? P0 solventnya bisa dicoret?
Bisa.
We cancel this, isn't it? So what's remaining is remaining here. X solute times P0 solvent. So this is delta P. So this is what I mentioned, the second formula that is important. This second formula is important. Sekarang kita bandingkan dengan the first formula tadi. The first formula was P solution is equal to X solvent time P0 solvent, isn't it? Now, when you compare these two formula, they are very similar, isn't it? Yang satu X solute dikali P0 solvent, yang satu lagi X solvent dikali P0 solvent. P0 solvent is the same, just the difference is the X. One of them is X solute, one of them is X solvent. When you put X solute, you are going to have lowering vapor pressure, which is the colligative properties. When you put X solvent, then it is become vapor pressure of the solution. Vapor pressure of the solution is not the colligative properties. Yang colligative properties yang atas ya, the delta P. The P solution is not the colligative properties, it's the vapor pressure of the solution. But the formula are very similar to each other. Just the difference is one of them is X solute, one of them is X solvent. Is it clear? All right, up to here. Do you have an equation, guys? Ada satu yang belum di sini ya, siapa? Coba dicek, mungkin nanti ada yang bilang itu ya, jaringannya. Oh, sini kah, Noval kah? Oh, sini, Mirza kah? Do you have Mirza here? Sekarang hilang 2. Yeah, Mirza have a problem, I think. All right. Is it clear, guys? All right. Can we continue? Okay. Now, let's do some, let's say, example here for the lowering temperature to make it clear. For example, here. Okay, I have 2 substance, glycol and let's say that's urea. And I have here the X value for them, X glycol and X urea. Glycol is 0.01, the mole fraction. Urea is also the same, 0.01. And now I have the value of delta P, the lowering vapor pressure. According to the data, for glycol, it is 0.18 millimeter mercury. Now my question is, what will be the delta P for urea? What will be the delta P for urea? Come on, guys, it's very simple. Ayo, come on. What will be delta P for urea? No calculation to answer. Yes, say something. If glycol and urea, they have the same mole fraction, 0.01 and 0.01, and the glycol delta P is 0.18. What will be the delta P for urea?
Same with delta P of glycol.
Very good. It is the same with the delta P of the glycol. Why it is the same, Alfie?
Because the pure pressure of solvent doesn't change. It's same with the glycol also, and the mole fraction it's same.
Yes.
With
The simple explanation is like this, Alfie. Delta P is the colligative properties, isn't it? I said that delta P is the colligative. This is lowering. It's a colligative, and colligative is only depends on what? Amount. And the amount are the same here. The amount is 0.01 and 0.01. If the amount are the same, no matter the type of the solution is glycol, urea, or any other solution, if the amount are the same, of course, the colligative properties also will be the same. Okay, is it clear? But if I'm asking you what is the P here, of course it will be different. Kalau yang ditanya P-nya, what is the P here? They will not be the same. I don't know the data, but it will not be the same. It's different. The P of glycol will be different than P urea because P is not colligative. Yeah? Is it clear?
Clear.
Everything is clear, guys?
Yes, sir.
Very good. Okay, so if I'm asking you, which one have a bigger vapor pressure? Pure water or seawater? Which one have
Water.
bigger vapor pressure? Pure water or seawater?
pure water.
Why pure water?
Because seawater it's is mixed with salt.
Okay, because
Doesn't pure. So
yeah,
the mole fraction of solvent is less than 1.
mhm.
So if the pure water has the mole fraction is 1. So if we calculate the vapor pressure between them, it's obviously the pure water has the higher vapor pressure than itu seawater, because the mole fraction, the difference of mole fraction between them.
Okay, so that of course pure water will be bigger than the seawater, yeah, because seawater is not pure anymore. Actually, there's a simple answer is that one, because seawater is not pure anymore. It's become solution because seawater is containing salt, so it has become solution. We know that the P0 solvent is always bigger than P solution. So that's why if we have pure water, which is the solvent, it always have bigger vapor pressure than the seawater, because the seawater is become the solution. That's why the solution is always lowering the vapor pressure. Okay, that's why solution is always lowering vapor pressure from the pure. Jadi kalau jadi larutan itu akan menurunkan tekanannya dari murninya. So the solution will lowering the vapor pressure from its pure solvent. And that lowering vapor pressure is the colligative properties. Itulah yang colligative properties, penurunannya. The lowering vapor pressure is the colligative properties, not the pressure of the solvent, not the pressure of the solution, but the lowering vapor pressure is the colligative.